In this video, we're going to look at how we go from just a conceptual understanding of electric potential, or the very specific definition of it in terms of electric potential energy per unit charge, and how we would calculate it for an arbitrary arrangement of charge. We'll look at point charges first, and then we'll look at uniform fields, and then we'll develop a relationship between the electric field and the potential. So when we start with point charge, right, positive Q here, and we're looking at a point in space near it, we already know that if we were to bring in a positive test charge, we could calculate the electric potential energy, and then we could divide out that test charge to get the potential at that point, right? KQ, Q naught over R Q naught, and that Q naught would cancel out, right? And so relatively simple for a point charge. We can check the units, we get a volt or a joule per coulomb, which is exactly what we expect for potential. If you have multiple point charges, you simply add up this effect for all of them. That's relatively straightforward if there's a limited number. It's a scalar, so we definitely want to know, is this a positive or negative potential? And then we add them up. You saw this yesterday, probably with that grid of 4 of them. You had 2 positives and 2 negatives, all the same distance from the central point, and so they added up to 0 potential in the end because you had 2 positive components, 2 negative, well, not even components, terms, and 2 negative components, right? So on the AP equation sheet, you see this 1 over 4 pi epsilon naught, which is K times the sum of Q over R, right? You're adding up the effect of a Q at a particular position, a charge at a particular position. So for example, if you had, this point charge, 2 microcoulombs, technically it's a spherical conductor, but we could talk about what is the potential at point A, point B, and right at the surface. That ends up being important as we go along, so we'll look at that. At A, it's KQ over RA, 18,000 volts. At B, it's KQ over RB, so 36,000 volts. We have double the radius or the distance R, and so that cuts the value in half, or doubles it, excuse me. We have half the distance and we double the voltage. At the surface, we have 180,000 volts, right? This is 10R is RA. So that's a tenth of the distance. So it's 10 times the potential. So we can actually take this and look at it graphically. And this is kind of that electrostatic landscape analogy, right? If you think of the positive charge as being sort of this little plateau or top of a hill, we get this 1 over R relationship going away from there. So at the surface, you're at your maximum potential. And I talked about this yesterday with some people. It was a question in class. Why is the top of this flat inside of a spherical conductor? And that's because inside, the potential doesn't change, right? You have to have the same potential on either side. And this is all about kind of the energy stored, the work required to bring it up to this point. We're going to talk a little bit more once we define the relationship between electric field and potential, and hopefully that will make more sense. This is an example that we had. We had an example very much like this in the packet yesterday, but this one is actually asking us to calculate the potential at this point, and it's not going to be 0 because we don't have 2 positives and 2 negatives. So the potential here is going to be the effect of 2 K2Q over R. And why? Well, that's because we've got 2 positives or 3 positives and 1 negative. And so the positive and negative cancel out their effects. We get the square root of 2 times A over 2, because that's how we get that distance along the diagonal there to the center. And once we have that kind of information set up, we can say, you've got an electric potential there, sure, but what about the electric field? Because the electric field is also an important thing for us to be able to figure out. And we already know a formula for that one as well. The difference, though, is that the electric field is a vector. And so the top left and bottom right corners have electric fields kind of pointing away from them, and those are going to cancel out. But then the bottom left has an electric field pointing away from it, and the top right has an electric field pointing toward it. So those two will add up. So basically, we need to find the effect of the electric field at point P from one charge and double it. So we've got 2 KQ over R squared. R is root 2 A over 2. or root 2 over 2a. So we square that. We end up with 4kq over a squared. And again, pointing up and to the right, this is, of course, a vector, not a scalar, so we need to actually include the direction. So this basic thing, the work with point charges and shells, can allow us to do some more interesting things. So we've got two charged objects, A and B. They both have the same positive Q on them, but they have different radii. And so if we want to know the potential at the surface, it's KQ over R or KQ over 2R. So twice the radius with the same amount of charge has half the potential at the surface, which hopefully makes some sense. Then we can do something like connect them with a wire. Well, what's going to happen? We know that the charge will flow as it does until there's zero electric field inside. But before we get to the zero electric field part, we also know that if everything is connected to itself and basically a wire, then the potential everywhere along that should be zero, right? There's no charge flowing. There's no current flowing after it rearranges itself. There's no resistor or light bulb in the middle, so it's not like we would have color coding different. If you think of the color coding analogy, every piece of metal connected to itself should have the same color or same potential. And so that means that the end result is that the current flows from high to low potential, so from A to B, because A has a higher potential, until the two potentials are the same. So then if that is true, if the new potentials are the same, what is the final charge on each sphere, right? Some of it's going to leave A and go to B. Well, we have KQA over R and KQB over 2R, right? Those are the charges on A and B. We know that most everything cancels out except for the charges and this factor of 2. So it means QB will have twice as much charge as A, or will be twice as big as A. And that, I think, makes some sense, right? If the charge is spread out as evenly as it can be on these two spheres, then it makes sense that the smaller one would have less charge. Before, they both had the same charge, and that meant A had more potential because it was more densely packed. Total charge is positive 2Q, which is what we had, where we had Q on one, Q on the other to begin with. So if you have 2Q and one of them has twice as much, we've got 4/3 Q and 2/3 Q on the other. So there's a little bit more to say about this. The electric field and the potential or potential difference. We know that the electric field lines and the lines of equipotential must be pointing or must be aligned perpendicular to each other. So with a spherical or radial symmetry here for our electric field lines, we're going to get a bunch of circles or in 1 dimension or 2 dimensions or spheres in 3. So that's the qualitative relationship, graphically, what's going on kind of visually. But what is the quantitative numerical relationship? For this, we need to go back to our energy unit, our energy curves discussion, where we said, well, if you've got a force, a conservative force that is providing that working against it, right, is what we do call the potential energy stored. We have this relationship that negative du dr equals that force. And so we can think about the electric force as the force we're dealing with here, and the change in potential energy as a change in electric potential energy. But we don't really want force. We really want force per coulomb electric field. And we don't really want energy. We want energy per coulomb. But that's convenient, because to do that, all we would have to do is divide both sides of this equation by Q, which is pretty straightforward, right? There's not much to that. So in order to do that, we get electric field is negative dV dr, right, by dividing through, or change in potential or potential difference is equal to negative dV dr, which is kind of nice. Not too different from what we've already done. It may not look exactly the same to you, and that's okay, but it is the same basic relationship that we have. So our old friends, relationship between work or stored potential energy and force, and our new friends, which is the relationship between electric field and potential. And this ends up being a really useful thing, especially when we're talking about potential is a thing, or potential difference is the thing we can just measure with a voltmeter. Electric field is not a thing we know how to measure, but now we can figure it out from something we can measure. The only real difference between these two sets of equations is one is force and energy. The other one is force per coulomb and energy per coulomb. So Going back to a simple diagram of this type that we've looked at before, we can ask ourselves, well, does this work? And we can think about this negative sign here. What is that all about? Well, the negative sign is really about the fact that as you move in the direction of the electric field, you move down in potential because we're using a positive test charge as our defining characteristic. So hopefully that makes sense. When you move with the electric field, you get a negative change in potential. If you go against the electric field, you get a positive change in potential, right? Uphill is against the electric field. Downhill is with the electric field. So let's do it. What's the potential difference from point P to infinity? Well, point P, right, is here at some distance from the the charged particle RP. And we want to integrate from there to infinity to find the potential difference. We know that the potential at infinity is 0. So if we know the potential at infinity and we know the difference between infinity and this point P, we can tell what that potential would be at that exact point. So we integrate from RP to infinity, KQ over R squared. That's the electric field, dr. And if you do that, you end up with negative KQ minus times negative 1 over R from RP to infinity. You plug that in, KQ over infinity is 0. Got that negative there, and you end up with a positive value. The two different negative signs kind of go away, right? And you end up with the change of potential from infinity into P is positive, from P out to infinity is negative because you're going downhill for one and uphill for the other, right? We can graph that as well, right? We can graph the potential, which we've already done, which is this hill. And now we can graph the electric field. We already know something about this, right? But we now know that the electric field, we certainly know the electric field inside is 0 because there's no change in potential with regard to that distance inside of the object. We have an electric field that's going to be pointing in the negative direction, right, to the left on one side and pointing in the positive direction on the other side. So the electric field is kind of pointing left and right of this particular point in space. And this leads us to uniform fields that are actually a lot simpler. What is the change in potential if we move through a uniform field? Well, a uniform field, right, is something we already know quite a bit about. We've learned that we can set them up by using a capacitor or an infinitely charged plate, which is what we usually use as our idea for one of those. And we can say that the change in potential is equal to the integral from A to B of the electric field dot dr. But what's true about the electric field here? Well, the electric field is a constant. So we're just integrating over a little bit of distance. And so that ends up just being the distance. So for a uniform field, the change in potential is negative of the electric field times the distance you travel along it. And so this is when you're going with the electric field in a nice uniform electric field. You have to be careful there, but that works very nicely. And again, this works for uniform fields only. The previous formula is for everything, which is always important to remember. You do have to watch out your signs, right? If you move in the direction of the electric field, you have a voltage drop, right? You're going down, downhill, so to speak. And if you move against the electric field, you have a voltage gain. So we can do a little calculation here that's kind of fun. If we move along this path, right, the voltage from 1 to 2 is going to be negative 1600 volts, right? 400 volts per meter times so many meters. That's, what's that, 4 meters there? Negative 1600 volts because we're going with the electric field downhill. From 2 to 3, it's 0 volts because we're going along a line of equipotential, right? From 3 to 4, we go uphill, 1200 volts. The stuff that goes perpendicular to the electric field is not going to require any work. You're not going to be doing work to push against it. So there's no change in potential energy per unit charge. And then going from 4 to 1, we're going uphill again, 400. And so the total change going around that loop back to the original point is 0 volts, which it should be, right? You're starting and ending in the same spot, which is exactly what you would expect, like that. So this is the loop rule. Even if there's no circuit there, the loop rule still holds, which which is kind of interesting. The loop is less clearly defined. We have to define it instead of it being based on a circuit path, but it still works. Another example from uniform electric fields. And so this is really getting into something that we're going to talk about called capacitors, right? Parallel plate capacitors. But we're going to start by saying, let's take two pieces of metal, separate them by 12 centimeters, attach a 60 volt potential across them. That may be due to a power supply or some kind of battery arrangement, 5 12 volt car batteries or something like that. A 60 volt battery charges two plates 12 meters apart. What is the electric field between the plates? And this, just to pause, is a really powerful calculation to be able to do. Because if you want to create a uniform electric field and you want to know how big that field is, if you have this relationship, you can just set up two pieces of metal a certain distance apart with a certain voltage, and you can say, this is what the electric field is in the middle of that. Obviously, there are some edge effects, but if they're relatively close together based on the size of the plate, it won't be a problem. So potential divided by distance, 60 volts divided by 12 centimeters or 12.12 meters gives us 500 volts per meter, which is, of course, an electric field rating. And that's exactly what we need to understand what the uniform electric field is. Inside. Now, we started with electric fields by saying, if electric fields are uniform, they do something to a charged particle that's similar to what happens to a mass in a uniform electric field. A little bit different, but pretty similar. And so if you were to take a proton, a positively charged particle, and place it near the positive plate and let it go, it would be accelerated across that in a uniform rate because it would have a constant force on it, and therefore you would have a constant acceleration. And we could just use kinematics, or we could use energy conservation to describe what's happening here. So if we do energy conservation, the initial kinetic energy is 0, and we're really interested in the final kinetic energy then being equal to the change in electric potential energy. We've got a negative here, right? Which makes sense. If the electric potential energy goes down, has a negative change, then we would get a positive final kinetic energy, which is good because you can't have a negative kinetic energy. We've got the charge of a proton is 1.6 times 10 to the negative 19 coulombs, positive, and a negative 60 volt change, right? Notice that we're going from positive to negative with the electric field. So that's a negative change in potential. And you end up with positive 9.6 times 10 to the negative 18 joules of kinetic energy at the end, or that's the amount by which the potential energy changed. You could also use Newton's laws here. You need to figure out a few things. You would first need to figure out what the acceleration was. For that, you would need to know the mass of the object. It's a proton. You can look it up. You know the electric field strength. You know the charge. You can figure out the force and go from there. So in summary, it is always true that the electric potential energy divided by a test charge, removing the charge that was there or that isn't really at that point in space, gives you the potential at a point in space. A change in potential is also always equal to the change in electric potential energy divided by that test charge. And we define the electric potential energy as a potential multiplied by a charge placed in that spot. Those things are always true. It is also always true that a change in potential energy is negative the integral of E dot dr, or the differential form, the electric field is equal to the negative dV dr. On the other hand, it is only true that you can do this kq over r and add up the effects for point charges, shells, and spheres. And you can only use this delta V is equal to negative ED for a uniform field. So we've got a uniform only, a point charge only, and then we've got a couple of several things, 5 different relationships. I mean, I would say really kind of 2 main ones that are always true. So when we're dealing with the electric field and talking about electric potential, we can find one and then use what we know about the physical setup to find the other. That's a pretty common thing we do.